While Thomas is setting up, I'll introduce our final speaker for the day. Our final speaker is Professor Thomas Heine from TU Dresden. He's a full professor of theoretical chemistry at the university, also a professor of theoretical chemistry at Yonsei University, Seoul, and the head of the theoretical chemistry group at the Institute of Resource Ecology at the Helmholtz Center in Dresden-Rossendorf. He graduated in 1999 from TU Dresden with a PhD in physics. And then he had extended postdoctoral studies, and he obtained his Venia Legendi in physical chemistry in TU Dresden in 2006. And he started first in the Jacobs University Bremen in 2008 as a professor, and eventually became a full professor there. From 2015 to 2018, he moved to Leipzig University, where he was the chair of theoretical chemistry. And then in 2018, he moved to Dresden and heads a group also in the Helmholtz Center. His research is at the interface of chemistry and physics and focuses on computational science of nanostructured materials. He's very well published, very accomplished, and of course you can read his biography. Most notably, he's a fellow of the Royal Society of Chemistry. The title of his talk today is The Chemistry Way Towards Quasi-Particle Physics. Thank you.
Yeah, Joyce, thank you so much. And well, I'm really excited to give that talk here today because when I prepared that, I was surprised. I've never given a talk in that state of Germany. I was born here, I was raised here, I did my A-levels here, I started to study here, but I was never giving a professional scientific talk here. So you are basically finishing with that here. So I'm very grateful for that. And yeah, so at the final talk of today's workshop, I would like to show you something a little bit more about materials. And so actually, you will see a little bit of chemistry and materials, but I hope there's still sufficient physics to keep you awake. And so what I'm showing you today, I call that the chemistry way towards quasi-particle physics. It really requires a thinking between the superposition of a chemist and of a physicist, right? So, and that's kind of the way my group and me, we are actually trying to work. So let me just find here a good position to, oh no, here we go. Okay, so I got the pointer. Good. So first, well, we had that introduction already. So my main affiliation is at TU Dresden, and we are working there quite a lot on framework materials. That's something that is very much on the molecular side. Two-dimensional polymers and two-dimensional morphs, which you probably know a little bit from Qin Yang's calculation, also very much on the chemistry side. I will dwell into that deeper during the talk, and also on two-dimensional semiconductors and the heterostructures. And at the Helmholtz group, which is located in Leipzig, actually, that branch, the Helmholtz Center is very much in radioactive waste management and so on, but they do some fundamental science, and that fundamental science is linking towards those subjects here, because it's going on actinide containing morphs, and that is quite useful if you want to understand actinide chemistry. And in order to understand that, we also have to develop there a little bit of DFT, because it's not working very well for these systems. The other part there is hydrogen isotope separation, where you have a lot of nuclear quantum effects, but I'm not going to talk about that today here. And at Yonsei, we are basically a little bit on ice due to the pandemic. I mean, I was starting there this collaboration with the IBS for nanomedicine with Jinwoo Cheon, and that's mainly on colloidal 2D semiconductors and biocompatibility. So I'm very often, you know, in chemistry, you don't have so much theory, right? I'm the only poor theorist in our chemistry department, and with my group. So whenever you are basically collaborating with someone, they are asking you for support, for understanding, but sometimes you can also make some good suggestions. So very often I'm just a link between different experimental groups, and I enjoy that very much, I have to say. So yeah, let me start with some content. Yeah, also, how are we actually pursuing applications? It's typically not the way that we say, oh, we would like to develop a topological photocatalyst, right? That's not the way we are thinking. We are thinking about, okay, you are going towards new materials. It's like the geologist who is entering some mountains, right? And the geologist is happy if he finds diamond, if he finds platinum, if he finds gold, or sometimes he finds nothing, right? Then he's not happy. So it's the same for us. I mean, we are looking at properties and what are the properties good for? So for example, they can be good for catalysis, for photovoltaics, for low power electronics, and so on, sensors. There's a lot of topology. I will talk today quite a bit about topology. And that means we are keeping our eyes open. And here's an example of what I mean. So I have a Humboldt fellow, Yalong Zhao, and his wife, Fengxiang Ma, she's in Shanghai. His project was to look at two-dimensional boron. Right? Borofene has been known in two-dimensional materials for a while. We know it's very unstable. So you can stabilize it by decorating it with metals. And one of the metals you can use is palladium. Okay? And if you put 4 palladiums per boron, you find a particularly stable phase. Okay, that would have been interesting, but not that interesting, right? If you look at that a little bit closer, you see that this system gets a bit corrugated. So that's the top view, that's the side view. You see this very strong corrugation here. And then we said, okay, let's have a look at these. So we had some trouble with the calculations. There were some things that were not converging when optimizing and so on. We looked into that a little bit more closely, and we realized that we found something brand new, a whole half-oxidic material. What does it mean? It doesn't matter if you pull it or if you compress it, it will always expand in the direction opposite to that. Has not been observed earlier, I think. And the reason why that is the case is because a Poisson number is basically going through 0 when you are at the equilibrium position, exactly at the equilibrium position. So something like that you can actually find on your journey. And that's something that is, I think, truly exciting. Okay, methods, right? Theorists in chemistry, you always ask what kind of methods are you using? Are you developing method? We actually try to avoid method development because there's a lot of stuff outside, but sometimes you simply cannot help it, right? Sometimes you just need a new method because there's nothing out there. So for example, when we started with these metal organic frameworks, there wasn't even a force field available that was treating them properly. So we had to work on that. We were working on some type binding method that is density functional based, and also there we needed to expand that to the periodic table to get a proper electronic description. Of course, for fundamental heterostructures, you need to have a good type binding approach. Now you find something, but when we started, there wasn't so much. We recently developed a method for bond breaking in periodic systems and so on. So I mean, we did there some contributions, and we actually push those contributions to big packages simply because you would like to have them available for the whole world. That's one thing. And the other thing is that you would like to have them working also in a couple of years after your PhD student has moved to some other place, right? And so here we are collaborating with quite a few people, sometimes via my senior colleagues, Thomas Bohme and Dorothea Golze, with Dennis Ruswiert from Berlin. Well, and of course, we have all this expertise in the group from force field to DFT and beyond in order to have, let's say, reasonable methods to treat those systems. Okay. Let me start a little bit with materials discovery. So we heard today about, let's say, large scale calculations of many different systems. Well, we did that quite a few years back when we didn't have these databases out yet. So we were very old fashioned, called this an atlas, right? An atlas of two-dimensional materials. And so if you look at that very old paper, which you can now find basically cannibalized all kind of different databases, you find quite resilience of band structures and band gaps and effective masses, etc. And and if you then look into that in a bit more detail, you find a few gaps. So one of them are noble metal dichalcogenides. So these materials have not really been considered at the time. They have been studied in the 1950s as bath materials in Norway, probably in very long winter nights. And when we looked into them, we realized, well, that's weird. We did our monolayer calculations. Oh, no, here we go. Pointer, where are you? Pointer is gone. Huh? Pointer. Are you dead? Okay, pointer is dead. Doesn't matter. I have to show like that. So you look into these materials and they are metallic as a bulk. You do a calculation of a monolayer and they get semiconducting. Okay, so Well, interesting. So we looked into that a little bit more careful. Okay, palladium disulfide, platinum disulfide, they are semiconducting. If you go to bilayer, one of them shrinks in the band gap very significantly, the other one gets metallic. I think that's pretty fantastic. So it's like, you know, you have something that looks like paper, you put a second piece of paper on that, it looks like aluminum foil, right? If you think about it, it's really cool. And well, we predicted that, and then only 1 year later, these things have been made. So we were super excited. So 2 Chinese groups were, you know, really pushing it, and they got it, and I was very happy that they did that. Then we thought, okay, what can we do with that? One of the topics here was low power electronics. Now just assume you can make an FET out of one and the same material. Okay, so you take the semiconducting area, which is your monolayer, and then you just put a bilayer and you make it metallic, and you have source and drain. Right? And then you can play with that, and you can simulate the characteristics of the FET, and you can see, okay, if you, pointer, are you back? Pointer's kind of back. Yeah. So pointer is kind of back, yeah. So if you play with the gate voltage, you can make it ohmic, right? And otherwise you have it looks like a diode and so on. It looks actually pretty nice, and you can do that. So a good question is palladium disulfide the only one who can do that? And what before that, you know, people took it up. Platinum diselenide is now kind of the new kid on the block of transition metal dicoagenides, and it's an excellent strain sensor. So we collaborated here with Max Lermer and Georg Duisberg, and they were building this nice device here, right? And you can actually measure strain at remarkable precision here. And the reason for that is simply that at the Fermi level, when you're straining platinum diselenide, you're changing the density of states very significantly. It's a very, very simple explanation for that. We got a project on that, we moved on, and we got a lot of difficulties from experiments. The reason for that was that it's very hard actually to get the very clean phase of platinum diselenide. There are a lot of allotropes. The allotropes are very close in energy, and so here the 2 left columns are on platinum diselenide. You can see here 2 different phases. They look very similar for a physicist maybe, but if you look at the chemistry, they're quite different, and they have very different electronic structures from metal to semiconducting, and also the number of layers gives you very different band structures. So that means that's the reason why it's hard in an experiment to get these structures. You have to be very, very careful in working on that. But of course, we have very good experimental colleagues, and they have that under control. Good. So are there more materials like that? Here's a very recent example, blue phosphorus. Blue phosphorin has been suggested by David Tomanek, has been made very recently. And so it's essentially, you think about graphene, you replace the carbons with phosphorus, but then you have some buckling. Okay, every second phosphorus is above the plane and every second is below the plane. That means that if you stack them together to a bilayer, you're not only having AA and AB, you also have to take care about the positions of these 2 atoms. And then you can actually look at them as a little mathematical problem. You find 7 structures, and we find 6 structures. As the 7th one has two local minima. You can calculate everything, and what you figure out is something very remarkable. The most stable bilayer is, contrary to the monolayer, metallic. That's weird. So that's also what the people at PRL thought. And well, I mean, it's really crazy, and let's hope that we can get that realized experimentally very soon. Black phosphorus is another one, right? Black phosphorus is really loved by device people, just as it is hated because if you have it to oxygen, exposed to oxygen, it will just corrode away. So you can stabilize that by putting germanium. And that phase here is known from experiment for decades, right? GEP3, right? You can find it, that's the bulk structure. And our question was, can you exfoliate that? Can you take off 1 layer, right? And then have a monolayer or bilayer, and what would be the properties? The properties would be very similar to black phosphorus, very narrow band gap, indirect semiconductor, something like 700 milli-electron volt band gap, very high mobility predicted. And if you go up to 3 layers, it becomes a metal. Okay, again, you have semiconductor metal transition in 1 material. So when you're looking at that one here, you say, well, okay, if I can put germanium, I can also put tin. And also that compound has been made very early. And we included that in our calculation. We just didn't include it in the paper because I talked to my local experimental colleague, Oli Oeckler, can you make that? And he said, well, we should be able to. Took him quite a while. Then we sent this to Johnny Coleman and Larry Nicolosi. They exfoliated, right? And they figured out, well, if you mix it with carbon nanotubes, you have an excellent lithium cathode. Okay, so it's an excellent lithium cathode. It has the highest aerial capacity reported to date. Okay, so that's something that you just find by chance on the way. So now let me come to solid tones. Okay, so now let's get a little bit more physical. So assume we have MOS2. And of course, we all know in MOS2, we have these Moiré bilayers. Now I have to play here a little bit because there are some videos included. So, and now what we all know is, right, you can put that in a certain degree, a certain angle, so that here is almost 4 degrees. And then you have the structural picture, and what you see behind are the solitons in a very poor man's representation. We are just putting the local density of states at the top of the conduction band, of the valence band, I'm sorry. And then you can change the twist angle, right? And you can see what the soliton is doing. So, I mean, this is essentially what you would actually expect, right? You change it, and you change, of course, the size of your unit cell, and there it changes. All great. There's one problem. That is one thing that you see very often in calculations. People took planar MOS2, put it on each other, and they were rotating it. But of course, reality is a little bit more complicated. You have a relaxation in the structure in Z direction. And that relaxation is very difficult to monitor experimentally, right? Because you simply don't have a mean to see that very easily. What happens if you include that simulation, if you include that in the calculation? So here you see the structure at this 4 degree, and your solitons are transformed to a honeycomb superlattice. Okay, so you don't have the soliton any longer. You have now something like a superlattice, and it stays like that. Right? It stays like that, and you will never have this very nice pure soliton regime. So what can you get now in experiment? That's something to be discussed. I mean, of course, if you think about encapsulation, maybe you end up on that side. If you have a freestanding material, maybe on a 10 grid or something like that, you're more on that side, and maybe you can actually flop from one to the other. Okay, now let me switch gears to go to, let's say, the more central part of my talk. And I would like to give, to take a journey now to molecular framework materials. And let me start with that. I want to show that slide because it's my first paper with Qin Liang. Qin Liang was still postdoc in Mainz, and I was still physics professor in Bremen, just starting, so to say, my career. And we were approached by Christoph, who is one of my close experimental colleagues. And he was making these metal organic frameworks, and you could grow these metal organic frameworks on a surface. And what is that? So you have here 2 metal atoms. They can be copper, zinc, and many others. I will only talk about copper today. And they can be arranged in a way that they can connect in 4 directions. And you can put a linker in between, and that can be a linear molecule. Right? And that linear molecule may have a certain length. And then you get this beautiful square lattice here, and that grows up here on the surface. And depending, I mean, these are experimental X-ray diffraction images, not powder, but X-ray diffraction images. So, and depending on how long is your linker molecule here, the larger is your pore. So that's the starting point. Okay, so we started with that. And soon afterwards, I got a phone call from Christoph. He said, no, Thomas, I have something I don't understand here. I take the simplest one of that series, the one with that linker. So this one here, that means it's this little morph here. So you just have a benzene molecule, and then you have this copper 2 oxide paddle wheel. Okay, I take this, I expose it to water vapor, and I see a magnetic response. And I can actually count 2 unpaired electrons per petal wheel. So each copper has an unpaired electron. And I don't understand it. And of course, Christoph is a very knowledgeable person. He knows that this petal wheel structure has been studied to death in quantum chemistry. And it is well known that people are calling this an antiferromagnetic singlet. Okay, one copper carries spin up, the other one carries a spin down. And because of that, you would never ever expect a ferromagnetic response or a magnetic response to an external field. Well, you would never ever do that because the coupling here is so strong that you don't find the right magnetic field in order to overcome that. So we looked into that, took us 2 years. And it actually shows you that the chemistry of those materials is sometimes really, really crucial. Actually, what happens is that the water kind of sneaks into the structure, dissociates binds to the copper atoms and makes some additional bridges, it looks like that then. So we have this kind of very intriguing structure. And we could confirm, well, we were predicting that. It was confirmed with infrared, with hydrogen, and with deuterated hydrogen. And oops, sorry. Then afterwards, I mean, they didn't believe that in Karlsruhe, so they developed a new X-ray diffraction technique. Okay, so they grew them off on a magnetite sphere in order to use the X-ray diffraction machine and then put Rietveld refinement in order to confirm that structure, and they did that. Well, afterwards, of course, you can then simulate the magnetic couplings, and you do then some very simple Heisenberg Hamiltonian and so on, and you predict the Curie temperature of 15 Kelvin, and that's roughly what you also measure in an experiment. So that means what I want to show you here is, or what I want to, the message here is, you have a molecular system, you just take molecular units, you stitch them together to form a solid, and you get magnetic ordering. Okay, we have a full magnetic ordering, we have a solid state effect in a molecular system. Can we do better? Yeah, we can. We can move on now and try to go to a semiconductor, which may sound trivial, but it's not that trivial if you think about it. So if you would like to make a semiconductor, and maybe you would like to have a semiconductor that is good for light absorption, then you think first, okay, I would like to take a molecule that is good for light absorption. And well, what do we think about then? Maybe porphyrins, right? These are the champs from nature. Let's take a porphyrin. And there's a very simple theory. Here, sorry. But there's a very simple theory about that, the so-called Gautaman model, which basically says in a porphyrin, you have 18 electrons that are on a circle. And if you calculate everything, then you get a very strong absorption, which we are calling this Moiré band. And that absorbs in the ultraviolet, so it's not too useful. And if you distort the perfect ring of 18 electrons, then you get additional absorption, the so-called Q bands. They are in the visible region. So that's what we would like to have. Okay. That means we somehow have to improve that. What can you do as a chemist? You can actually start now playing with chemistry. You can put metals inside, you can put functional groups somewhere, whatever. And we were basically benchmarking with our theories, okay, for those kind of models. And then you can actually think about, okay, let's build them off. And that's the way it works. So you take now these molecules, and you grow them on a surface. And at the end of the day, you get a structure that looks like that. You have a layered structure, you have here these paddle wheels. So here you would have the porphyrins in between. You can see the porphyrins much better here from the top view. And then the question is, okay, what would be the band structure? You do a calculation on that. And first you say, well, okay, that really looks like I have no interaction at all, right? You can see here a band structure, and the band structure is just flat, super boring, right? If you zoom in, you see a little bit of dispersion. And I was surprised myself that you can actually prove that this is becoming an indirect bandgap semiconductor. Right? If you look at that, that's the conduction band, that's the valence band. Now it gets an indirect semiconductor. And that direction here is along the stacking. And you can actually also prove that experimentally, as Hickey has done that. And that was very nice, but of course, it was only a start. You have to be better with getting this band dispersion stronger in order to make a real semiconductor. And you can do that, right? You can take here now different porphyrins. And what first we were thinking like a chemist, right? I mean, we would have to distort our ring. You can do that by replacing hydrogen by boron. What happens is you shift your absorption from the ultraviolet to something like the far infrared, right? You can also put fluorine. That didn't have any effect. It was a bad idea. Or you can actually extend some additional molecules. And what you can see here in the solid line, that is the ultraviolet as a UV vis spectrum, so the light absorption from the molecules, and the dashed dotted line is the light absorption of the solid. And you can see that the one in the center has a very strong response. The question is why? You do a band structure calculation, you realize why. Here and here, we have very poor band dispersion, but here we have a very strong band dispersion. If you look very closely, you see again that the direction along the stacking, right? And if you look along the stacking and you zoom in, that you can see here that these porphyrins, which are our linkers, stack the same way as you would have the carbon units in graphite. Okay, so you have the same kind of stacking like graphite that gives you that dispersion. The dispersion gives you indirect bandgap. It also gives you redshift. It's exactly what you would like to have. That's the way you can actually tailor such a material. Good. So now let me come to that part here. And this is, in a way, I mean, I was very much intrigued by Ronnie's talk today when he was coming here with his circuits. And I think there's maybe some similarity, I don't know. That's something that really triggers me at the moment. That's, can we actually create topological networks that are beyond what we find in nature? Right? If you go to mathematics, you can find different networks. I mean, you have a complete series of something like 200 networks in 2 dimensions. In 3 dimensions, many, many more. And in nature, you don't find all of them realized. And in particular, you don't find them realized that your Fermi level is at that point where your topology is actually interesting, right? We heard just now that there are, I don't know, 80% of all materials are have topological bands, right? The point is, you would like to have the Fermi level at the right place. Can we do that? And I would like to show you that we can if we do a little bit of chemistry. So we all know graphene, very, very simple slide. Why do we have a Dirac in graphene? The reason for that is we have a honeycomb lattice. It's not because of carbon, but it's because carbon makes a honeycomb lattice, and that we have 1 electron left, so per carbon atom, that is actually making this pi system. That pi system forms this very beautiful Dirac structure. And if we include spin-orbit coupling, then we actually see the band gap opening, we can see the topological state, etc. So that is very easily understood with graphene. So it's basically a lattice property and not the property of the individual atom. So that means we have to utilize the lattice in order to do the topology. But in order to do that, we need to have the right chemistry to realize a lattice. Okay, and that's essentially the core of the message here. So most simple thing, right? I mean, you only have to think about the most simple interactions. We have lattice sites, they have a chemical potential or an on-site element. You have interactions with the next neighbors, possibly with the second next neighbors. You write down a very simple tight binding Hamiltonian, includes spin-orbit coupling using Haldane model, for example. So essentially, that's the implementation of what you basically had in your circuit, right? I mean, it's nothing else. And now you can apply that. I mean, this is, of course, for graphene, right? No spin-orbit coupling, you just see a Dirac point. You put on spin-orbit coupling, you have a tiny gap opening. You get Scher numbers that are different from 0. So that means you have topological materials. You can also do the nano ribbon, and then you can see these topological edge states. Everything is nice, everything is very easy. And of course, it's very well understood. What about other lattices? What kind of properties do these structures offer, right? And if you want, it's very simple, right? I mean, just take the stuff and you assume that each of the points here is a carbon atom. Of course, you cannot realize it like that, but just, you know, for the sake of the argument, let's just do that, right? And okay, HCB, so the honeycomb we know, right? So this already is very well known. Simple hexagonal would always be a metal. Simple square would always be a metal. I mean, you have here this very interesting feature, it's the X point. We didn't discuss it so far. I mean, something for future research. You can go to Kagome. You go to Kagome, you have a Dirac and a topological flat band. Okay, you can go more complicated. Forget about that one for the moment; it's too complicated. You can go for LEAP because LEAP is very much appreciated in physics. You have a flat band which crosses exactly Dirac. Okay, so now, well, can you realize it? Yeah, well, first here again. So just to show the topology, in the Kagome we really have topological bands throughout, right? We exaggerate here a little bit the spin-orbit term, therefore it looks a bit distorted. If you would just take the regular spin-orbit term for carbon, it would be much less. If we go to the LEAP lattice, we have a trivial flat band and also non-trivial Dirac bands. Good. So can you realize that? And you can do that, right? I mean, you can also play with it a little bit. If you you have here in the LEAP lattice, you have the center one that has 4 neighbors, and that one has only 2 neighbors. If you change the chemical potential a little bit, you can fix the flat band either to the conduction band or to the valence band. So you can play a lot with that. But what you can do in physics is, well, you do the brute force approach. You take a clean surface, copper 111, you cool it down with liquid helium, then you're placing atoms, either chlorines as shown here on the left, or carbon monoxide as shown here on the right. You can place it on it, and then you can actually prove that the band structure is what you have, that you have all these fascinating properties. Alternatively, you could also use photonic lattices, so that's all there, that's all great. But I don't want to go through the LEAP at the moment. I would like to go through the Kagome because that's actually very rich. You know, Kagome coming from these baskets, these Japanese baskets, and it looks like that. And the Kagome lattice is very much related to the honeycomb lattice. So essentially, if you put a lattice point in the center of the triangle, you have a honeycomb, right? So both of them are very much related. And how can you create such a Kagome lattice? Now I'm coming to the direction here. Of course, you have to find molecules that make it. And you need triangles. So you look up what kind of triangular molecules you have. You find triangulines. Okay, so very simple. And so you find these triangulines, and you can actually commercially get them, and you have them, right? I mean, there are many, many different ones. What is important is you can functionalize them. You can change the center atom, and you can change the bridge. The rest you don't want to touch. Okay, and the center atom can be, we were using boron, carbon, or nitrogen, and the bridge atom is, the bridge group is not so important at the moment. It's just fine-tuning the electronic structure. And if you do that and you arrange them in such a two-dimensional polymer, you get something pretty cool. So assume first that in the center we are putting a carbon. And the whole molecule is a radical, it's a single radical. So essentially you have the same situation as in a honeycomb lattice as in graphene. When you get a band structure with a Dirac, well, that's just a scheme here. I will show you afterwards that the scheme is very close to reality. We have a Dirac here, right? And this Dirac is at the Fermi level, and you have something like a 7 times magnified graphene. Nothing else. Great. So now you replace the carbon by boron. That means you take away 1 electron per building block. That means your Fermi level moves down. Now you have a flat band that marks the valence band max. That means you have very, very heavy holes, and you have very mobile electrons. Okay, if you replace the carbon with a nitrogen, you do exactly the opposite. You completely fill now this Dirac band is full of electrons. You put the Fermi level here. Again, you have now very mobile holes and very heavy electrons. So that was quite interesting. We looked into that, and if you put the atomistic realization, you really see what we were predicting in this very first, very simple place. Okay, just here for some examples to convince you. So here in this particular COF, we have an effective mass of the electrons of 0.44, and we have 23 for these very heavy holes. Right here, for the carbon system, the Dirac is always directly at the Fermi level. And here for the nitrogen ones, here you would have electrons of 150 electron masses, but half electron mass for the holes. So that's, wow, interesting. You can tune your semiconductor, you can make very polar semiconductors that are either only conducting electrons or if they are only conducting just holes. And well, okay, we published that, and then just, okay, we were asked these flat bands, you know, we have seen before flat bands in the MOFs. And these flat bands were super boring because they just showed the units didn't interact. Is that now a flat band because units are not interacting? Or is it a real flat band where we have a full conjugation? And we looked into that, and we do have the full conjugation. We really have these flat bands. So then just last year, so we were asked about explaining that a little bit more in detail, and we really showed here. I mean, here you have the honeycomb lattice, and here you have the Kagome lattice. But here you have the very simple tight binding band structure, and here you have the two-dimensional polymer. I'm just highlighting here the honeycomb elements and the Kagome elements, and that here is a fat band calculation showing at the projection here, and you can really see that those two lattices are reflected in this real polymer band structure. And then it has been made. So I was very happy. Also, there was this paper last year where they have a new technique, this hot dosing technique for making these monolayers of these two-dimensional polymers. And they were confirming both the Dirac bands and the flat bands experimentally. So we were very happy about that. Okay, you can also do a little bit of chemistry. I don't want to go here too much into detail because the time is running. So of course, you can also think about, are they useful for chemistry? And for example, Claudia Felser is very much interested in topological catalysis. And that's what we tried here. Could these materials be very good photocatalysts? And if you want to do that, right, you really have to do all the, you have to calculate the overpotentials and the band positions. By doing that, you have to calculate all these very boring chemical reactions here. So it's a lot of tedious work. right? But one can do that. And if one is doing that, one really can show that if you pick the right of these polymers, you can implement a very interesting device. Namely, you couple now in 2 electrodes the photocatalyst. On one side, you harvest an electron, you harvest a photon, right, from a flat band. It goes to a very conductive band. And without overpotential, you have the oxygen evolution reaction. Then you just link the one electrode with another electrode electrically. You even gain a little bit of energy, so half a volt. And then you harvest a second photon, right? And you move it up here, and there you can run the hydrogen evolution reaction without overpotential, and you would have basically a tandem device for photocatalysis. So that means you can bring these very interesting polymers also towards an application. Good. So now we have seen one example where one can do this Kagome lattice in experiment with quite a bit of effort, but can we do that also for others? And I was very lucky that something like 8 years ago, Rahul Banerjee's group was very strongly advancing, was one of the groups that very strongly advancing these layered covalent organic frameworks, which are essentially the same type of the polymers that we were discussing here before. And at that time, it was very important to get these structures experimentally realized at all. I think also Qinliang was very active at that time. Also Donglin Zhang was very active at that time. And it was a lot of synthetic work. And we were contributing here basically with characterization and structural understanding and things like that. But then, I mean, of course, in the idea course, you can realize all of that. We just have to decompose the essential elements of those networks. Okay, you have a 6-fold or 6-fold with a 2-fold or 3-fold or 3-fold with a 2-fold, whatever, all these kind of things. And with those ones, you can construct all the lattices that you wish. I just gave you 4 examples, but of course you can go through all the lattices that mathematically are possible in this world, right? All of them we can create using chemistry if we just find the right building blocks for each of these individual structures here. And here are just a few exemplary ones. There are many, many more. Well, there's infinite possibility if you want. And well, then you have to put that together. And that is a work together with Donglin Zhang. So that paper here involved something like 10,000 calculations and 100 synthesis. I mean, the poor, very industrious PhD students of Donglin, they were working really, really hard. And it shows you what is possible with chemistry here. So assume that you would like to make a honeycomb, you can do that, right? You combine here a knot with 3 neighbors and a linker with only 2 neighbors, and that looks great. But what if you would like to distort your honeycomb? Okay, then you just take 2 different linkers and it works. Or maybe you want to distort it even more. You take 3 different linkers. Or you go from your square network and you would like to make a rectangular one. Okay, you can all do that, and it's not only PowerPoint, it really works. I mean, the 100 materials here are published in this in this paper, and just that you have an idea how it looks like. That's one of the honeycombs, and you can see that it is made of the same units. Just the amount of different linkers. So you see you have 4 of these red groups, and you have only 2 of the red groups. For compensation, we have 4 of the blue groups, and here you have only 2 of the blue groups. You can actually make these networks. There's one problem though. These materials are electronically super boring. And the reason for that is again chemistry, because we were linking them with these boron oxide units. And these boron oxide units are something like hard walls for the electrons. They don't communicate with each other. So we have to get rid of those. And with that, so there was actually a competition between Qinliang and Donglin. So they basically proposed the same reaction in order to make a fully conjugated 2-dimensional polymer. So here, all the electrons in the whole system can talk to each other. They can interact with each other, and they form then this beautiful structure. And well, we published that paper there. Qinliang published that paper here. But with that paper, we basically closed the journey from the molecular framework to a real 2-dimensional semiconductor. By you can make these regular assemblies of molecules, but that doesn't really help you, because then the properties of the network have very little or no impact on the materials properties. In order to get these materials properties from the network, what you need to do is you need to make all the electrons in the system communicate with each other. And this you can do with the right chemical reactions and an organic matter. That means you have to achieve conjugation. And it was neither Donglin nor Qinliang who had that idea first. We figured out that it actually came from Roald Hoffmann and Woodward and Wangbo from the 1970s. I mean, that was, made peace in the community. Anyway, the idea is very clear, right? In order to have a semiconductor, we need to have bands, and in order to have bands, we need to have the electrons communicating, and I think we can achieve that now with chemistry. So let me close. Okay, what properties do such structures offer? I mean, we have found quite a few, but I'm pretty sure there are quite a few more. We don't know yet what we are going to find because there are still so many nets in 2 dimensions, and I didn't even talk yet about 3 dimensions, right? In 3 dimensions, you can basically play exactly the same game. That is still something to be explored. Good. So just a few topics to close what we are working on these days. So there is another difference if you think about a traditional semiconductor and a molecular semiconductor, and that is how would a grain boundary look like? Right? Grain boundaries are awful, right? We don't like them. And but if you are having a molecule, you have a big advantage because you can actually distort them a little bit. It doesn't cost you too much energy. That means you don't have dangling bonds, right? You don't have all these nasty electronic states that distort your properties. They are all very well behaved if you do it properly, and we could actually simulate all these kind of little tiny things that you can see here in this excellent TEM picture, and that's actually quite nice. So with Qinliang, we are fighting really complicated structures. So he's keeping my people busy. He is always having these fascinating new chemical reactions that are making 2-dimensional materials, and very often we don't really know the atomistically detailed structure, and it goes from making a hypothesis, proving or disproving it, and going back and forth. That's a lot of fun here in the synthetic part of the work, but also in the work where we are actually going now towards more effects that are physically interesting, like MOF magnets, right? Or high mobility band like charge transport and a semiconducting 2-dimensional MOF. And I'm enjoying that very much. And I would like to close with the last part, and that last part are heterostructures. Of course, you can make all kinds of heterostructures, but of course, you can make heterostructures of 2D polymers and 2D crystals. Like these ones here have been made, right? So these are done in Qinliang's group, and we were also looking into them a little bit. So it's what you would expect. But what would we expect from them? We are investigating that right now in various projects. So you can ask the question, how does the superlattice impact the electronic structure of the graphene or of the 2D polymer? So what is the electronic interlayer coupling? Electron-phonon interactions would be super interesting, right? Other magic twist angles, we don't know yet, right? And what about other materials than graphene? And so one of the things that is really super intriguing, assume now you have a couple of layers of your 2-dimensional polymer, like a 2D COF, you put graphene on top of that or some other 2-dimensional crystal, then what you're getting is something like a phonon quantum dot, right? You have basically something like you have this grid, right? Think about the honeycomb lattice or any other lattice, and you put something on top which can oscillate, and then you have these phonon quantum dots. The question is, what frequencies would we have? Can we use them, for example, as a mass sensor? Probably we can. Would they talk to each other, right? I mean, what would be the hopping between these quantum dots? Can we do some physics out of that? So it's actually quite interesting and to be explored. So with that, I would like to wrap up and acknowledge. So actually the take-home message here is I was discussing 2 mechanisms with which we can control the electronic structure of materials. I was only focusing on 2D materials, but of course, other materials may be also possible. One of them is stacking and twisted stacking of 2-dimensional crystals. And the other one are topological lattices that are made by molecular building units. And with that, we can actually go beyond what nature offers in terms of materials. We can actually implement anything that is mathematically possible in a material. And with that possibility, of course, we can increase the range of potential quasi-particles, interactions, etc., that we would like to understand. And yeah, that's something what we are very much interested in. I think we are at the very beginning of that research. And where we would like to end up with is, of course, that we have a rational design of topological materials that is, let's say, really very intuitive and get, for example, topological materials with very large band gaps. So challenges are certainly there. I think at the moment they are almost more on the experimental side than on the theoretical side, because one of the most important thing is that you have a high crystallinity, low defect density, but also that you have suitable monomers or post-synthetic functionalization that you can have these active lattice points that make all these interactions. So my main collaboration partners are here. So Qingyang and Renhao in their groups in Dresden, Christoph Völl in Karlsruhe, Rahul Banerjee, who moved to Kolkata, Dongin Zhang in Singapore, Yu Jing in Nanjing, and Jiwoo Cheon in Seoul. And actually last year, just before the pandemic started, we had a retreat right here in Halle, my group in front of the youth hostel here in Halle, so just 1 year ago. So happy to show that picture. It's also our last group picture. And yeah, and I thank all these guys here for funding. And I thank you very much for your kind attention, of course. I'm happy to take questions.
So we have time for a few questions. See news.
Okay, thanks, Thomas, for this very nice talk. I have two questions. The first one is related to these Kagome lattices that you showed us. So they're very interesting because they have these intriguing flat bands that we also know from just the bilayer graphene at the magic angle. So is there already some expectation what kind of correlated phenomena, or if there are some sort of correlated phenomena expected when the Fermi level is tuned or gated?
So
energy?
Now at the moment we are looking at two things. The first thing what we wanted to look at is the topological catalysis. I showed you here the photocatalysis with the Kagome. And I was very much intrigued. Is it the topological property, or is it just the fact that we have a flat band? Unfortunately, it's just the fact that we have a flat band. So how did we figure that in a very rabiatic way? We did the calculation with and without spin orbit coupling. Okay, so having then basically the topological characteristics on and off. So yeah, it's an extremely good question. So and we didn't explore it yet. That's something that we have to. Okay.
Maybe if I may, one follow-up, is it? Yeah, okay. So generally, I mean, this whole field of 2D materials, there's a very large combinatorial space now with these MOFs and COFs. The combinatorial space gets even larger. Now you also want to build heterostructures. It's even larger. Mm-hmm. So in the beginning, you motivated your talk a little bit with the serendipitous discoveries. Is that really the most rational way forward, or so what's the best way to explore that large space?
Okay, in terms of lattice structure, if you look, for example, at the class of transition metal chalcogenides, you have very few representatives there. And many of them are also very similar. I mean, if you take tungsten diselenide and molybdenum disulfide, of course, chemically, they are very much different, but in principle, they have the same features in there, right? Even if you go to the tellurides. So in all these materials, you don't have the possibility to go to those materials where you have these many topologically active bands that are at a point where we can access them by shifting the Fermi level to the right point. And what I wanted to highlight here is that if we are building together molecules, these molecules can have significantly different chemical potentials. So changing in each of the monomers, for example, a carbon to boron or carbon to nitrogen, is not doping. I mean, it's really shifting the Fermi level by, in this case, because we have two scatterers, by 2 electrons per unit cell up or down. So that means we can really use the chemistry to bring the Fermi level exactly where we want to have it. Right? And I think that's a great potential here, which we don't have with natural materials. What can you do with a natural material? You can put a gate voltage, but that's brute force, right? You can dope, but that creates you some more charge carriers. It doesn't really it doesn't really change the main characteristics. I mean, of course, an electrical engineer will not very strongly disagree with me, but
Exactly.
but
Anyway.
but I mean, doped silicon still somehow is silicon, right? And here we change the entire character of the material by these very tiny functionalizations, and that I think is the opportunity that we are having. That using this very large space that organic chemistry has developed for us and bringing that diversity towards the materials, that gives a huge opportunity. And of course, we can concentrate to a few lattice types. Let's say we are only looking at LEAP. So we get in love with porphyrins of phthalocyanines, which have these 4 connections, and we go for the LEAP lattice. And we put a similar effort than we were putting to, let's say, MOS2. And I think we will discover a lot of fascinating physics there, right? And that's where I would like to push a little bit.
Good. Thank you very much. It was a very inspiring talk. Let me make a parenthesis here. So the much of what you explained reminds me a little bit of the field of cold atoms, where you can choose your lattice because you can put the lasers however you want, but then you're stuck with a very long length scale, and that gives you just Hubbard interactions if you want to think of interacting physics. Now, you have one advantage over cold atoms. The cold atoms always float in vacuum, right? There's no way around that, but you can put stuff on, you know, on some substrate. Yep. Can you explain a little bit more what possibilities are experimentally feasible in terms of substrates? Can one also use bulk materials, superconductors, things like that?
Okay, so let me first try to answer the first part of the question. Second part, we didn't explore that very much. I mean, it's a pretty new field. But for the first part of the interaction, that's exactly the point. So we want to have something that is room temperature stable and not something that you can explore now and next moment your sample is gone, right? So so therefore these polymers are of course great because they are much more stable than these cold atoms, as you explained that. And now the question is, are these interaction lengths too long? And if you think now about graphene, right? In graphene, if you look along these kind of Dirac bands, you are on the 2-3 electron volt scale, right? So here in the one that I was showing, these Kagomis, we are on the something like a little bit less than 1 electron volt scale, right? So it's less, but it's much, much more than nothing. Simply because if you put these atoms on a grid, there's no chemical interaction. Okay, so it's kind of mutual polarization or whatever you're having there, the interaction is very, very weak. Here, the interaction is much stronger because, I mean, also if you think about that, if you would take now this Kagome lattice that I was showing, this polymer, and you just put a lattice of carbon atoms at the positions of the center atoms, you would end up with something which is very similar to these cold atoms that you mentioned. But because you are providing this pi space, you delocalize your scattering centers significantly. They get much, much larger and they really overlap and they really interact. And therefore we have this very large dispersion. And that's the trick. And in a way, we are lucky that we can do that, right? And we know now how we make these to communicate. This pi interaction, as in graphene, can get very long range. And we can exploit that.
Excellent talk. I actually have 2 questions, but I'll try and be succinct. So the first is, I saw in a couple of cases that you have transition metals. How do you incorporate the effects of those without something like a reduced density matrix or, a 2RDM method essentially to get the correlations?
Well, I mean, the correlations in things like MOS2 and so on, they are not that strong. Right? I mean, we simply don't.
But if you have transition metal complexes, and again, this is, for example, folks who are working in embedding theories, et cetera, really think about how to get the metal complex really, really well. So how do you?
If you look at these, for example, at these Moiré, you have these paddle wheels, right? Where you have a perfect example on that one. There, essentially, what you have to do is you have to know your enemy and you have to know how to get away with it. I mean, there's no way to apply the right theory to treat these gigantic systems at the fundamental level you would like to. So you can work with broken symmetry DFT, for example, just to mimic the right states. Or you can—
Without the multi-reference nature of the state, you wouldn't necessarily be able to describe a transition metal complex.
These ones you can. I mean, you can take any characterization from experiment and we nail it down to a really good extent. You have to, I mean, of course, sometimes you have error compensation. I mean, if you look at that, if you fundamentally look at this, I mean, okay, very crazy one is a nickel pedal, right? Where you really have a nasty problem of two paired electrons, no, 2 unpaired electrons per nickel that are interacting in a very weird way. And these ones are, let's say, if you do a DFT calculation, you know that you do something wrong, right? But you get a result and you know how to work with that. And now you take this one and you put that into some other system, and you know that you will do exactly the same thing wrong. So basically, you eliminate a systematic error. If you want to do it right, you take the complex and you go towards multi-reference methods and do the proper job, and then you know the difference. And that difference will basically be very similar to the whole system. Essentially, now I explained what QMM is, right? But that's roughly what we try to do. I mean, we try to be realistic, because if we want to describe everything in a perfect way, then we would simply not be able to advance at the pace that we are doing.
Okay, my second question, if I may, is, so with these MOFs or COFs, could these be used as hosts for molecular qubits? And what are your thinking? What's your thinking on that? I know some people say yes and some people say no, so just wondering what your thoughts are.
I have to be honest, I don't know. I don't know. I mean, we are at the moment now realizing them at the right way. And once we have done that, if we describe them properly, then of course we have to go for the next step. I think at the moment, we didn't think about that. Okay.
Talk about it some more.
Yeah, definitely.
So there's a question. But Stuart and I both have a question. Is there a question? This chat. Maybe, Amokar. Let's give it to Amokar, Stuart. Yeah. So Amokar, and this will be the last question since we don't have time, and we'll talk to Thomas after, Stuart and I. So Amokar asks, I would think that the experimental band structure mapping of chemical systems like MOFs and COFs is a very challenging task. Could you comment on methods used by chemists to map Dirac or flat bands, for example, materials in solution? And in order to use physical methods such as ARPIS, how much is the progress going on for MOFs and 2D, for designing MOFs and 2D structures?
Okay, complex question, right? So one part is, well, I mean, I think chemists and quantum matter physicists are not that much different in the methods they are using. So there's a lot of DFT, but there are methods beyond that that we are employing, and we always try to use what is, let's say, feasible, right? I mean, of course, you cannot do GW or RPA for everything, right? So that's one part. ARPIS, I have seen it. I mean, okay, what do you need for ARPIS? For ARPIS, you need to have a rather large area of a material which is aligned, right? Because your light spot needs to grasp that. And the first example and the most striking one is in this Nature Materials paper from last year from the Galeotti group. No, Contini group, I'm sorry, Galeotti was the first author. I was talking to them how they achieved that. I mean, you can achieve it, but it's hard. What you need to do is you need to be able that your 2D polymer grows in a way that all the crystal domains are aligned. And if you manage with that, then you can measure ARPIS. And we have now, for the first few 2D polymers, we have now showcases that it works. Right, and I think then it's only a matter of time that will become maybe not a standard method, but a method that gets much more applied than it is today.
Okay, so thank you. Thank you so much for this wonderful talk, and also thank you to all the speakers today. Applause for everybody. It was very interesting, a very good learning experience also for myself. With that, then our workshop it's ending. So thank you so much for attending in person and online. We hope to see you again soon. Thank you.